Okay, I'm going to tell you how to find vector calculus identities, because divergence and curl are not always enough, and sometimes you need more complicated machinery. And in particular, the ones that I'm interested in discussing today are the divergence of f times a vector field. You can imagine if f is a constant, it would factor out. So you have f times divergence of f, but now there's going to be plus an f not constant term. And this will just be the gradient of f dotted with f. So you can think of this as a product rule. And there's going to be something similar for the curl. And remember, these are actually just the dot products with the gradient operator. And so that should help you see why there's a product rule. Just think of this as a one-dimensional derivative. So the curl will have something very similar looking. It will look like f, the constant term, and then you'll have the curl of f, and then finally you will have that gradient term. Instead of the dot product, we will now have a cross product. This is the f, not a constant term. And again, this is effectively just a product rule. So I'm going to show you two ways you can get this identity, because oftentimes in your work you will have to figure it out. But I think there's a very nice way to do it. First, I'm going to show you how to look it up on Wikipedia. And I'm serious, because this page is actually so useful. I refer back to it many times in my own work. So I'm going to switch over to the internet. And if you just Google or search in your favorite search engine, just vector calculus identities, you get this very nice Wikipedia page, which has been here for 5 years at least, and it is quite comprehensive. It has basically everything you need if you're working in 2 and 3 dimensions. And I'm most interested in the section which is summary of important identities, which I'm going to click, because now I just list everything in one compact space. So notice that the gradient has product rules, but what I talked about just now was this divergence identity, where they're using C and A instead of F and F. So you notice that first there's the constant term, and there's the non-constant term. And similarly, if you scroll down to curl, you see there is a product rule as well. This product rule has the constant term, C, plus if C is not a constant, you have to add an extra term. And there's really all kinds of nice product rules. This one in particular, where you have the curl of two cross products, this definitely shows up. I believe the divergence of a cross product also shows up. And one you will also probably like is, where is it? The curl of a curl. Yeah, this is an extremely important one. This arises actually in electromagnetism. So now that you know that this page exists, feel free to refer to it to find a particularly nasty identity. But I'm going to show you how you can derive some of these identities yourself if you do not have access to the internet. So I'm going to say quicker ways to derive this. Because you, other than expanding all the terms and regrouping, which to me sounds quite painful, because you've seen how large the cross products can be. So I suggest not doing that. And I think my approach that I'm going to try to show you is to just consider f equals a times I. So just a vector pointing in one direction. This is totally enough. And then, what you will do is you will get simpler expressions. You will get simple expressions. And then you're going to rewrite them using f. You're going to want to rewrite them using the gradient of little f, and not objects like p or ddx, which depend on our simplifying assumption. So if you can get away with just these objects as in our identities that we have here, now this will be good enough. And the reason it's good enough is effectively that you can take any vector and that's pointing in a bad direction, and then you just rotate it to a good direction. But I won't go into the mathematical proof of that, but it seems plausible, I hope. So let's talk about the divergence, because that's the easier one. So the divergence, I'm going to use my simplifying assumption to get the divergence. Now we're just doing f times a. So this is actually a lot simpler, because now really we just have ddx of f a. So clearly now this is just f dA dx plus a df dx. But now I want to rewrite this using our vectors. So we have a couple of vectors available to us. We have the gradient, which is fx, fy, fz. We have capital F, which we know is just a, 0, 0. And so notice that the dot product is just a times fx. And that is exactly this term right here. This is gradient little f dot capital F. So notice how I rewrote this just using little f and capital F, and there's no simplifying assumption. So this is not simple. That's good. That means it's general. So now we just have to deal with, what do we do with this last term? Well, remember this is just the constant term, like I mentioned before, if f were constant. So this should just be f times the divergence of f. And is that true? Well, the divergence of f, we need just one more calculation. The divergence is del dot ai. So this is just dA dx, which is exactly what we want. So this is del dot f. Therefore, we end up with f divergence of capital F plus the gradient of little f dotted with capital F. That's exactly what we wanted. And the difference between just expanding only one partial derivative, that's all we needed. We did not need ddy or ddz. So this is a little more helpful. So let us try the curl. This is, I think, where the method actually becomes non-trivial, because I think the divergence was easy to see. So let us try to do the curl. So what we really want, again, is to show that the cross product of this will have a product rule. And I think the second term, where you have that gradient of f, that is the hard term. So somehow we'll be trying to get this term using our simplified representation. So let's now use the simplifying representation. So the curl, remember our simplifying assumption was simply that f is one direction. So the curl of this will now be the curl of fai. So we can actually get a lot of mileage if we know what the curl of this kind of thing looks like. So what if I just call this thing G? let's compute the curl of gi. So this is I think the hardest calculation we need to do. This is I, j, k, ddx, ddy, ddz, and g, 0, 0. So here is where we're using our simplifying assumption. This eliminates a lot of terms. So now I'm going to expand on g. What that means is I'm going to circle that g, and I'm going to delete all the other rows and columns that match g. So you'll have g times the remaining determinant. So you'll have a j, you'll have a k, you'll have a ddy, you'll have a ddz. And this is legal because this is 2 rows away. So if I went here, I would put a -1. If I went here, I would put a -1. I have 2 -1s. That's obviously a +1. So let's do it. We have j times gz minus k times gy. That is the curl of this thing. So what we need to do now is I'm going to rewrite this thing now using vectors. Now that we did the hardest calculation, we want to rewrite this. So we have a couple of vectors available to us. So we obviously have I. We have the gradient of g. So what happens if we take I cross the gradient of g? It's a natural thing to do. So this is I cross gxi plus gyj plus gzk. Notice that these can't. The first term is 0. I cross I is certainly 0. And I cross j is k. And I cross k by the right-hand rule should be minus j. So we end up just with gyk minus gz. J, that is really similar to what we have. There's just this minus sign. So this is just minus I cross gradient g. How about we just put that gradient g cross I? So this is what the curl of this thing is. So it is gradient g cross I. Therefore, let's now plug it back in. So we're going to use our calculation with g. So let's do gradient g, which is now fa, cross I. That's what we showed. That was what that work was for. So now I'm going to use the product rule because it's just begging. This term is just begging to be used with the product rule, right? Whenever you see ddx of fa, you know what to do with that. So this is now gradient f times a plus f gradient a cross I. I'm going to split this up. So gradient f cross ai plus gradient a cross I, and then we have this f on the outside. So this thing we know what to do. This is actually capital F, because again we want to rewrite using vectors. Okay, so this actually is our first term here, or our second term. So we're almost done. We just need to show this equality. Because we have that f on the outside. So these are clearly, they should correspond to the same thing. So is it true that the gradient, rather the curl of capital F is gradient A cross I? It actually is true, because that's exactly what we did up here. Because remember, F is just AI. So if I plug in A for G, I surely should get this. So therefore, we have established what we wanted to show. Okay. Why am I'm telling you this in case you come across an identity and you need to figure out how to prove it. You don't have access to the vector calculus identity sheet. The lesson of this is just to use a single direction and to try to rewrite it after you've simplified this nice compact expression. You rewrite it now in terms of what you want to show. Thanks for watching.